Welcome to Graph It Out. In the previous session, we looked at the proof for cos x plus y, which gave us an expression in terms of cos x, cos y, and sin x and sin y. In today's session, we are going to look at a different proof, but we will reach the same result. The difference is that we are going to use instead of using the coordinates and the Euclidean distance calculation, we are going to use the sin x and cos x directly, sin x, cos x, all those terms directly. And that will give us the lengths we require, and that will give us the final result. Now keep in mind that in this channel we try to always base our proofs based on a set of graphs, and also we try to keep things a bit informal here. If you need the formal stuff, you can find them from various textbooks. There is no point in us doing the formal stuff. So that does mean that every now and then we make a few mistakes here and there, and if you find any egregious mistakes, please point that out. So today's graph, as usual, you can go to this repository and you will be able to find the link to the graph. I will provide a link to this repository in the video description. So the link we need is this one, cos x plus y proof 2. And you will see this graph. This is the graph for today's proof. You can think of it like the skeleton of today's proof. At the top we have the dependencies, and then we go to the start, and then after that we look at all these steps. So the first dependency is that you should know about sine, cos, etc. So if you are watching this video, you probably already know about that. So this part is covered. Basic angle calculations. So imagine that I give you a set of parallel lines and another line that cuts them at an angle. Now what all those angles are going to be the same? What all angles will add up to pi? What all angles add up to 2 pi? You should know about that. And if you know these two, then you can continue to the proof. So what exactly are we going to prove today? We want to find an expression for cos x plus y in terms of cos and sine of x and y. Now we are trying to have a direct approach which does not include any kind of Euclidean distance calculation. So we already saw a proof for this in the previous session, but in that proof we found out the coordinates of a set of points, and then we used Euclidean distance calculation to come to the expression that we were looking for. But in this proof, we are going to use the definition of sine and cosine directly to get the lengths and the final expression. So there are a few steps before we go to the main diagram. First one, multiplication of cosines. So the basic idea is when do we see expressions like this? When do we see multiplications of cosines? So I have given a diagram here, and if you look at this diagram, we can come to this kind of terms. So origin is sitting here, and a bunch of points P1, P2, P3, P4, they are all at length 1 from origin. And there are some angles sitting here. And here is the basic idea that when this length is, let's say 1, this is cos x1. And to make the notation easier, I'm calling it C1. So Ci is cos xi. So if you drop it perpendicular from P1 onto OP2, let's call that point Q2, then OQ2 is cos x1. And if you repeat again the same, you get cos x1 times cos x2. And you drop a perpendicular again from that Q3, you get Q4, and you get one more cosine term, cos x1 times cos x2 times cos x3. This is the basic idea. So just drop perpendiculars and build on the top of the previous length calculated, and then these terms keep multiplying. Now let's look at the same for sines. Multiplication of sines, how do we get these terms? So let's start with this diagram over here. OP1 is of length 1, and this angle is x0. So this opposite side to to x0 is going to be s0. So si is sine xi. So this is sine x0. Now we're going to put angles here. And let's see what that gives us. So if this is x0 and if this angle is x1, this is s0 times sine of x1. That is s0 times s1. And for x2, again, the same thing happens. And for x3, again, the same thing happens. So the sine terms gets multiplied. Now we had cosines and we had sines. So let's put all of them together to get this multiplication of sines and cosines. So first look at this triangle OAP. That's the main one. If this is x1 and if this length is 1, then this is cos x1 and this is sine x1. Again, remember this notation that I'm using. And these two lengths can be built on the top of S1. How? We know this angle is x3, then this is the adjacent side, so S1 times cos of x3, and this is the opposite side, S1 times sine of S3. And we can do the same for here. Then everything will be built on the top of cos x1. Cos x1, cos x2, cos x1, sine x2. So when you see diagrams like this and a bunch of angles, you should be able to understand how to get each length based on a set of multiplications of sine and cosines. That's the basic idea. Now let's go to the main diagram. We have a bunch of diagrams, so it's not a single diagram. But let me explain what's going on here. So starting point, think of origin and this angle x. And P2 is corresponding to this angle x. This length is 1. So this circle that you see here is of radius 1. And then we are adding another angle y. So this total angle is x plus y, and this P1 corresponds to x plus y. That's why the x coordinate of that. So if you drop a perpendicular from P1 onto the x-axis, you get the x coordinate, which is cos x plus y. Now, how do we get to this point Q, which is the point corresponding to P1 on x-axis? How do we get this Q based on the non-other points here? So let's drop a perpendicular from P2 to the x-axis, and yeah, like this, and it will reach the point R, and we can see that OR is cos x. Now all we have to do is to find this distance. The issue is that if we take this approach, G has coordinates in terms of cos x plus y, and we will not get rid of that easily. So we cannot proceed this way. We have to find another option. So here the idea is that we start from P1 and we drop a perpendicular onto OP2, and then we do again a perpendicular onto the x-axis. So you get cos y times cos x. So OR is cos y times cos x. Now what remains is this D. If we can find this D, then we know how to reach Q. So for that, look at this T sitting here happily. So this T is eyeing this P1Q. And we can drop a perpendicular from T to P1Q. And then we can do some magic to get that length. And then that length is same as the length of D. How do we do that? We need to find this angle for it. So that's what we're going to do here. Let's draw all this diagram, and the important thing is this magenta line segment over here. If this angle is x, since this magenta line segment is parallel to the x-axis, this angle is also x. And we know that this is perpendicular because we were dropping a perpendicular from P1 onto OP2. Which means this angle over here is 90 degree minus x, or pi by 2 minus x in terms of radian. And we know that this is perpendicular, so this angle is x. So this beta sitting here is x. Now let's remove all this clutter and redraw the diagram. We get this, where we know that this angle is x. What is P1T? So this is 1 and this angle is y, and this is the opposite side. So P1T is sine y. And now we know this angle. What is ut? Ut is this times sine of x, which means this was sine y, this is sine of x, so sine y times sine x. Ut is that, which is same as t, which is same as q1. So now we know how to reach q. We go to OR using cos x cos y and then reduce sine x sine y from that to reach q. So cos x plus y, this length is cos y cos x, which is OR, minus sine y sine x, which is this d. So this is the proof for cos x plus y in terms of these particular terms. Now whenever we see a result like this, we should always ask where did this minus come from. Here we got this minus because of the fact that we have to reduce QR from this total length. Now this proof is somewhat limited because we took all the angles in the first quadrant, and we don't really know how it's going to get generalized for other quadrants, so this is limited, but the proof is a lot more visually appealing. Just by looking at the diagram itself, we can say that this is cos y cos x plus, not plus, minus sine y sine x. So try it out and let me know how it goes. Thank you for your time.